Hey everybody, Dr. Retzek here. This is our second video in section 15.5, where we're trying to get our minds wrapped around the idea of triple integrals. Let's get started. So I thought what we could do today is a concrete example where we're handed the triple integral to do, but we don't like the order in which it was handed to us. And so it's incumbent on us to change the order and keep track of the corresponding limits of integration. So here's the example. We're being asked to compute a triple integral 0 to 1, 0 to 1, x squared to 1, 12x z e to the zy squared, all done, dy dx dz. So that's the problem. This comes out to some number. This integral comes out to something. Maybe it represents something physical, maybe it doesn't. But our job at this moment is to see what this integral comes out to. Now, before we get any further into switching the limits, let's talk about why we might want to. I think the issue is here. If you want to do this innermost integral, which is how everything would start, you would be integrating with respect to y. X and z are constants as far as y is concerned. And so basically you're integrating e to the y squared dy. And that integral is super hard, if not impossible. It's not clear how to even start with that innermost integral if this is the order of integration. So right off the bat, I feel like I want to label that integral as impossible. Which makes me want to switch the limits of integration. Because I'm imagining if the inside integral were done, say, dx, then this would be no problem. Because all you got in there is x to the first, and then a bunch of stuff that's constant as far as x is concerned. So if the inside integral were dx, we'd be in business. But it's not, it's dy. So we have to switch it around. Now, this is an interesting exercise because in order to switch it around, we have to understand what is this region of integration. With the limits in this order, what is the chunk of 3D space over which we are being asked to do the integral? All the clues are there in that purple box, but we have to duplicate that region so that we have a prayer of turning the limits into the different orders. Okay, so what we want to do is we want to try to draw the region over which we're doing this triple integral. Okay, so here's my thinking. Let's do it messy at first, and then we'll try to produce a really pretty picture, and then from that pretty picture, we'll try to actually change the order of integration and do the problem. Okay, so let's not even worry, and let's just make it messy first. Okay, so this is happening in the Xyz coordinate system. We know that much. So let's just give ourselves an Xyz coordinate system. So X is out of the screen. Y is pointing to the right, like usual. z pointing up. Okay, let's try to read off these limits of integration. Focus on the z first. Z runs 0 to 1. Okay, so we get to pick any z we want between 0 and 1. Okay, so z's are chosen in there, 0 to 1. The next limit of integration, the next variable, is the x. And it looks like for each choice of z between 0 and 1, we get to choose any x we want between 0 and 1. So imagine a z right here. Some typical z between 0 and 1. And then we get to choose an x anywhere we want between 0 and 1 for that z. And that's true for any z between 0 and 1. And so the z's and x's that are in play are a square. So those outer two variables of integration are just chosen anywhere in that square. Now, having chosen an x and a z in that square, that 1 by 1 square, look at that last variable of integration. Y runs from x squared to 1. So imagine we were down at z equals 0 and say this x. What if we were here in the square? What if we were there? Those innermost limits of integration tell us, all right, well, the y variable kicks in at x squared. The y variable kicks in at x squared and then kicks out at 1. Now, depending on where the x is, the y will kick in at different locations. If you had an x, say, near 0 down here, then the y would kick in much sooner. Say, like there. But every time, the y stops out at 1. So this is where y stops every time, but where y starts is on this parabola. So that curve right there is y equals x squared. And the fact that these innermost limits of integration, the x squared to 1, they have no z's in them, that fact means, oh, so the innermost limits of integration are independent of z. So at any x, no matter what the z is, at any x, the y has the same variation. Starts at x squared, stops at 1. So that means that's all parabola. So this is a curvy vertical wall right here, floating above y equals x squared. This is a back vertical wall right here, and this is a flat rooftop, and that's the region. Okay, let's see if we can redraw it super clean. So here's my attempt at the super clean region. You got the XYZ coordinate system, X, Y, Z. You got the region. All right, that back corner's on there for sure. That top back edge, that front back edge, that front edge, this vertical front edge, and then this is rounded like that. That is our region. All this. That is the 3D object we're trying to integrate over. Okay, so that's our object. This curve right here, that's y equals x squared, flat in the xy plane. That's y equals 1. That's z equals 1. And this is x equals 1. All right, so that's our shape. Now that we have the shape, now we have to try to write down the limits of integration for an order of integration that suits us better than the originally given order of integration. So remember, come back up here to the integral as it was given. We did not like that order because the very innermost integral, the one we would have to do first if we were going to actually do this problem, was being done with respect to y. And that integral just looks too hard with respect to y. All right, now the easiest of the three variables as far as the innermost integral is concerned looks like x to me. Y was no good, and if we did z, I think we could do z, but it would be integration by parts because we basically have z e to the z. But that x, it's just an x to the first. So I really vote. I vote for x on the inside. And if we're going to do x on the inside, maybe we should just swap x and y. Let's just leave z alone. No reason to bring z further into the earlier integrals that I can see. And if we're wrong, we'll just amend our decision later. I think we should go like this. Let's get those two swapped. Let's put x on the inside and y in the middle. Okay, so brand new problem now. We got to look at our region and just shoot for this order of integration. So it's going to be an integral, an integral, an integral. The function is 12xz e to the zy squared. And we are shooting for dx first, then dy, then dz. Okay, here we go. Let's talk about z's. Z is the outermost variable of integration. Look at that shaded gray region and say to yourself, what z's are in play? All right, the z's that are in play still 0 to 1. So those outermost limits of integration, we're going to keep 0 to 1. Now, for each such z, let's talk about the y's that are in play. For each such z, y runs back here from 0 until we get to 1. So we're looking at the shadow of this region in the yz plane. So as far as variable y is concerned, y's run 0 to 1. Now, here's the payoff. For each such choice of a z and a y, like say here, for that choice there of a z and a y, let's talk about what x does. X starts at 0, kicks in back there in the yz plane, and runs forward until you hit that curved vertical wall at y equals x squared. So that green segment is starting back in the YZ plane and coming out of the screen towards you until it hits that curved vertical wall, y equals x squared. Therefore, if we are interested in x's variation, given a choice of y and z, we see that x runs from 0. All right, well, it's out to that curved wall, which is y equals x squared, which is x equals root y positive square root, because this is coming out towards us in the positive x direction. So x runs 0 to root y. Okay, so what's happened so far? We were given some integral to do. We figured out the region of integration, but we did not like the order of integration. Knowing the region of integration, we were free to change the order. We went with dx dy dz just because it looked like this innermost integral with respect to x is going to be a walk in the park because z and y are constant as far as x is concerned. All right, all that's left now is carrying out the integral. So let's see if we can do it. Remember, innermost integral first. Let's see, integrating with respect to x, that's going to give us 6x squared z e to the zy squared, evaluated from x equals 0 to x equals root y. Haven't touched the middle or outer integral yet. All right, let's plug in. Outer two integrals, nothing's happened yet. Upper limit, when x is root y, you get 6yz e to the zy squared. When x is 0, you get nothing. So 6yz e to the zy squared dy dz. Now we're to the middle integral. This is the one with respect to variable y. And you can see our choice to put dx innermost has had a very, very nice effect, because now we can fire up u substitution on this integral. Let u equal zy squared, then du, remember, z is constant as far as this middle integral is concerned, is 2zy dy. Therefore, okay, outer integral hasn't happened yet. Inner integral, we haven't done the integral yet. We've done a u sub on that integral. So let's see what that u sub amounts to. All right, there's going to be some limits of integration. The whole thing's being done du now. We'll worry about those limits in a second. Let's figure out what the function transforms to. So du is 2zy dy, and here's a zy dy. So I think we got 3 e to the u du. And the new limits of integration focus right here. When y is 0, so is u. And when y is 1, u is z. All right, well, we're cooking. Let's do that inside integral now, straightforward. It's just 3e to the u. 3e to the u from u equals 0 to u equals z. And so it's all down to, what, 3 integral 0 to 1 e to the z minus 1, e to the 0, which is 1. And that integral, oh, that's just a peach. So we got e to the z, take away z, evaluated z equals 0 to z equals 1. So all told, 3. All right, let's talk about inside the brackets. That's e to the 1 minus 1. Take away e to the 0 minus 0. So all told, e minus 2. And that is the number answer to the very, very original integral, gotten by wisely switching the order of integration. So that's it on that example, and it illustrates that we're in charge, and often one of the 6 orders of integration is far superior to the others. And in this case, I think the key thing was having x on the inside first. It made that innermost integral easy and really set up the u sub to deal with the exponential. Okay, I think the drawing is tricky on these, and I think reading off from the regions what the limits of integration are is also a little bit tricky. Practice, ask questions, and I'll see you guys soon. Bye.